All right, so like I was saying, we are continuing on with our lecture from last week about chemical equilibrium. And really, it is an extension of what we were talking about with chemical kinetics, except now we're going to jump into the part where reactions don't actually go to completion, right? They come to this point called equilibrium, and where the rates are the same of making the products and the reactants, and then the concentrations are the same after equilibrium point for the products and the reactants, and all that fun jazz, right? So let's just keep on going from last week, okay? So deducing equilibrium concentrations, right? So how do you figure out what a concentration of a product or reactant is at equilibrium? And these are the steps that you have to take. And I'll go through these, one by one, and we'll figure it out all together, right? The first thing you got to figure out, right? The first thing you got to do is you got to tabulate all the known initial equilibrium concentrations, right? So that stuff is the stuff that's going to be in your problem, in the word problem that we give you. Okay. Okay. After that, for anything for which an initial or an equilibrium concentration known, you got to calculate the change, right? So that change means how much of the initial has gone away, right? Initial concentrations have gone away, and how much of the new stuff has come in, right? Has been made. And use the initial concentrations to find the equilibrium concentrations of all the species, and then calculate the equilibrium constant using the equilibrium concentrations, okay? So these five things here, these are the five steps, and it seems a little complicated, but we distill it all down to this thing that we call the ICE table, and I'll show you what the ICE table is in a second. And I'll tell you now that the ICE table is the bane of every Gen Chem student's existence, because we'll use the ICE table for many, many things for the rest of the semester, right? But it's the easiest way to organize all your equilibrium concentrations, right? So one more time, tabulate all the known concentrations of the equilibrium and the initial. For anything for which the initial and the equilibrium concentration is known, calculate its change. Use a balance equation to find the change for all the other products and reactants. Then use the concentration and changes to find equilibrium concentration for all species. And then calculate the equilibrium constant using the equilibrium concentrations. Okay, so your first question for today is this. Which of the following steps are involved in deducing an equilibrium concentration? And it's an easy one for the first one. Most of the questions today will be easy. And while you guys are signing in, I'll sign in as well. Oh my God. I promise I work here. Just stop asking me for all this information. Three, three, 3796. Yes, that is definitely me. Thank you very much. Thank you very much. Save, even though you never save. And then all my forms. Oops. That's already been done. Here it is, the Deucing K. We got 8 people responded so far. I'm sure there's more people. There's 10 of you in here? Yes, there's 10 of you, so we need 2 more people. One more person, please. There's still 10 people, though, right? Yeah. Still waiting for that last person. There it is. There's that last person. And that last person answered correctly. No, wait. I don't know who they did. Anyway, so I don't know if they did or not, actually. It looked like it changed, but it didn't change. Anyway, so the distribution is this. Which of the following is deducing the separate concentrations? Actually, the answer is D. All of them were steps in deducing the equilibrium concentrations. Okay, all of them were steps. So, and I know I have all these steps written out pretty clearly here for you, right? In this little spot right here, right? But let's go through and do an example of how to do a equilibrium concentration. All right. So here's an example of a question I might give you on a written portion of an exam, right? On the written portion of an exam. A closed system initially containing 1 times 10 to the negative 3 molar hydrogen gas and 2 times 10 to the negative 3 molar iodine gas, right, at 448 degrees Celsius is allowed to reach equilibrium. An analysis of the equilibrium mixture shows that the concentration of hydrogen iodide is 1.87 times 10 to the negative 3 molar. Calculate what Kc is, which is the equilibrium constant, right, at this temperature for the reaction taking place, which is this. Okay, so I was just saying before, right? This is when we introduced to you this thing called the ice table, right? And it's the bane of all Gen Chem students' existence because we use it for almost every single thing from this point forward, right? And the reason why it's called the ice table is because I stands for initial concentration, right? C stands for the change in concentration, right? And then the E stands for at equilibrium, right? Or equilibrium concentration, okay? So the way you set up this ice table so that you can answer so many different questions in life, I guess in your chemistry life rather, right, is you put the reactants over here on the front end right here. So these are all reactants, right? And then this is the product, product. No, product. Oh, well, I'll just cross it out and write it correctly. How about product? There we go. That's the product of this reaction. Okay, so we've got hydrogen gas up there, and that's in molar. We've got iodine gas up there, that's in molar. Those are the two reactants. And then over here we have the product, which is hydrogen iodide gas, and that's in molar as well, and that's our product, right? And then the way we fill out this chart, this ice table, right, is we fill it up with the things that's been given to us. Okay, the things that have been given us, right? So we go back to our problem here. It tells us that the initial concentration of hydrogen gas is 1 times 10 to the negative 3, right? And it tells us that the initial concentration of iodine gas is 2 times 10 to the negative 3, right? So that's what we put there. Okay, we put here initially, right, for hydrogen gas, 1 times 10 to the negative 3. And initially, we have 2 times 10 to the negative 3, right? And then, of course, since this is initial and no reaction has occurred yet, what do we put here for concentration of hydrogen iodide? 0, right? Because no hydrogen iodide has been made yet at the initial step, okay? And then the other piece of information that we're given is that when the reaction goes to completion, or not completion, but goes to equilibrium, right, the concentration of hydrogen iodide gas is 1.87 times 10 to the negative 3. And so this number here is what goes here, right? Because at equilibrium, hydrogen iodide gas, right, is 1.8 times 1.87 times 10 to the negative 3, right? So that's how you start out doing an ice table, okay? You plug in all the stuff that you know. You plug in all the stuff that you know, okay? The next thing you can do is you can start filling in the rest. So what's the change here then, right? What do we put in change? Well, we know that we began with 0 moles, right, or 0 molar hydrogen iodide gas. And at equilibrium, it was 1.87 times 10 to the negative 3 of hydrogen gas. I'm sorry, not hydrogen gas, hydrogen iodide gas, right? So then we know that the change, right, the change from 0 to this is that same number because you went from 0 to 1.87 times 10 to the negative 3. So the change is then plus, right? The change is then plus 1.87 times 10 to the negative 3, right? Because you're getting more of it, and that's why it's plus. That's why it's plus, right? So right now I'm going to go ahead and tell you that when you're doing these ice tables, just remember this is ice, right? This is always reactants right here. and this is always the products right here. And so generally you always divide it down the middle like that. Sometimes there'll be less or more, right? Reactants or products, but we always divide it down the middle. And the reason why I do that is because if this is going to be the side where you get stuff, right? Because it's the product side, the change is positive, then that means over here on the left side, these changes will always be negative, right? These changes will always be negative because you're losing, right? You're losing hydrogen gas and you're losing iodine gas, right? You're losing iodine gas. So how do we figure out then? How do we figure out then what these changes are, right? For equilibrium concentration for the hydrogen gas and the iodine gas? Well, we got to go back to doing our molar calculations, right? Remember our molar calculations from Gen Chem 1? Okay. So we'll do hydrogen gas first, okay? We're told that at equilibrium, right, we have 1.87 times 10 to the negative 3 concentration moles of hydrogen iodide, okay? So we can start out by saying that. 1.87 times 10 to the negative 3 moles, right, of hydrogen iodide, right? But remember when we say molar, like big M molar, what does that actually mean? That means number of moles over liters, right? That's a concentration. So we can easily put it over 1 liter right there, right? Just like that, okay? And then we continue our fence posts or our dimensional analysis, right? For every, so remember that also the equation is right there too. So don't forget your stoichiometry, right? For every 1 mole of hydrogen gas, you get 2 moles of hydrogen iodide. For every 1 mole of iodide gas, you get 2 moles of hydrogen iodide, right? So don't forget that you have the stoichiometry right here. Those are all ones. That's a 2 right there. Okay, so going back to our dimensional analysis, right? We have to get rid of moles somehow. How do we get rid of moles? Well, for every 2 moles, right? Every 2 moles of hydrogen iodide, right? For every 2 moles of hydrogen iodide, we get 1 mole of hydrogen gas, right? And that will give us a number. And we have to do the same exact thing again for the iodine gas. Now we're lucky in this problem because both the iodine and the hydrogen gas have 1s as their coefficients. So they're probably going to come out, not probably, they will come out to the same number. But it's not always like that, right? It really depends on the stoichiometry. But just for giggles, 1.87 times 10 to negative 3 molar. Oh, I forgot to put HI up there. HI, right? 1 liter, okay? And then for every 2 moles of HI, we get 1 mole of I, right? And then that gives us a number, okay? That gives us a number. That gives us a number. And I won't ask you to do the calculation for me right now because I did it already. Actually, I had a calculator with me. Oh, I gave it to Kimberly. That's all right. She's got my calculator, but that's okay. This should come out to be 9.35 times 10 to the negative 4. And this one should also come out to be 9.35 times 10 to the negative 4, right? So those right there, right, are the changes in the concentrations, right, for both hydrogen iodide and for, no, sorry, not hydrogen iodide, for hydrogen gas and iodine gas at equilibrium. So we already know that this is supposed to be a negative sign right here, right? That's what we're losing. And then we put into our box 9.35 times 10 to the negative 4, 9.35 times 10 to the negative 4. Okay? Does that make sense? How we get those numbers right there? Right? Easy little molar calculation at the bottom that you've done a gazillion times in Gen Chem 1, right? Right? Easy little molar calculation to do the change in the reactants, okay? So to make sure that I'm right, I did already uh, go forward and typed it in for you so you could read it better, right? So there we go. It's 9.35 times 10 to the negative 4, negative 9.35 times 10 to the negative 4, right? Sounds good. Sounds good. So now the question is, right? Now the question is, how do we figure out what's at equilibrium then? Anyone know? What is the concentration then of hydrogen gas and iodine gas at equilibrium? Exactly. That's exactly right. You just subtract this number from that number and this number from that number, right? Because of this, these are the changes, right? That's what's missing. That's what's going away, right? And so all you have to do is subtract 9.35 times 10 to the negative 4 from 1.00 times 10 to the negative 3, and then also do the same thing over here. Subtract 9.35 times 10 to the negative 4 from 2.00 times 10 to the negative 3, and then you get the concentrations at equilibrium. It's a great time, right? And so doing that calculation gets you this, right? So now you have a completed ice table, right? It's a completed ice table that shows you the initial concentrations of the reactions, shows you the change, right? And then at the equilibrium, it shows you what the concentration of each is. At equilibrium, the concentration of hydrogen gas is 6.5 times 10 to the negative 5. Iodine gas is 1.06, uh, 1.065 times 10 to the negative 3. And then we already knew this from the question, right, which is 1.87 times 10 to the negative 3 for the concentration of equilibrium at hydrogen iodide, okay? Which is great, right? Which is great. The rest of it is easy because the rest of it is plug and chug. If you recall from the last lecture, right, the equilibrium constant is always what? There's always, equilibrium constant is always the products over the reactants, right? Right? The equilibrium constant is always the products over the reactants, okay? And remember that we had 2 moles of hydrogen iodide gas, that's why it's squared at the top, right? And then for each of the moles of hydrogen gas and iodine gas, they're all 1 each, so they're at the bottom, right? Literally, that's all it is, products over reactants, right? Don't forget that, that's important, right? And all we have to do now is plug in these numbers here, the equilibrium numbers, right? Plug in those equilibrium numbers right there that we got at the bottom into this equation, right? Into this equation. So that's a 1.87 times 10 to the negative 3 squared. Don't forget the squared, right? And then that's the equilibrium concentration of hydrogen iodide at the end of the equilibrium. And then we have the concentrations of both hydrogen gas here and iodine gas, right? Iodine gas there from the bottom of the ice table, right? Just to remind you, this is the H2 concentration at equilibrium. This is the I2 concentration at equilibrium. And this was the HI concentration at equilibrium, right? And you just do that math, right? So don't forget please excuse my dear Aunt Sally, because you're going to get this wrong if you don't follow the order of operations. You have to square this first, right? So square these numbers first. Then you have to multiply these numbers by each other first, right? And then you divide them, right? Because the order of operations is that multiplication comes before what? Division does, right? So don't forget to do it that way. Otherwise, you get the wrong answer. All right, so here's your next question. How do you determine the change in H2 and I2 in the ice table? It's the same as HI by subtracting HI from the initials by carrying out the molar concentration calculations using stoichiometry, or none of the above is correct. Okay, okay. Let's see here. There we are. Got 3 responses so far. So far, most of you are getting it correct. Still need 3 more people. 2 more people. Two more people still. 1 more person. One more person, and they're there. Okay. Wow, we got an answer for every single one of them this time. All right, so here's the distribution. Here's the distribution right here, right? There's all 4 colors are present right now, but that's okay. The vast majority of you got that one correct right there. The answer is in fact C, right? The answer is C because if you recall from the previous slide when I was going through this whole thing, right? To get the change in I and H, right? You had to go through your molar calculation using stoichiometry to get those numbers, right? So the other one, the other answer that was there was subtracting from the initial. Remember that? That doesn't happen until after you get these numbers, right? And that's finding the equilibrium concentration. So finding the change requires the stoichiometry calculation. Okay. Any questions so far? I know this is riveting stuff. It's good stuff. Okay, so let's keep on trucking along here. In a mixture, sorry, is a mixture in equilibrium? Is a mixture in equilibrium question? Okay. Which way does the reaction go? Okay. To answer these questions, oh, I get you. They're 2 separate questions. Okay. Is the mixture in equilibrium? That's the first question. Which way does the reaction go? That's the second question, right? So to answer these questions is we look at this thing called Q, right? This thing called Q, and Q stands for the reaction quotient, right? It stands for the reaction quotient, and Q actually looks a lot like the K, the equilibrium constant, right? But you use Q to figure out concentrations at certain conditions, right? At current conditions. Not necessarily at equilibrium, but at different times, different points of the reaction, okay? To calculate Q, you have to substitute the concentrations or the pressures of the reactants and products at any given time during the reaction into the equilibrium expression. So don't get confused, right? The Q expression is going to be the exact same thing as the KEQ, or the equilibrium concentration expression. The only difference is that for K, you'll have the concentrations of all the equilibriums, right? Whereas for Q, you'll have the concentrations that are given to you at a certain point in the reaction. Okay, so those are 2 different things, and we'll go over an example in just a second. So nature wants K to equal Q. Why? Because Q is equilibrium. Sorry, K is at the point where it's equilibrium, right? And so everybody wants to be at equilibrium, right? They're most stable that way, right? The reaction is, effectively over, right? You've got the same rate of reaction forward and reverse, same number of concentration of products and reactants, right? So everybody or nature wants Q to equal to K, right? So if Q is less than K, nature will make the reactions proceed to the products, right? So here's an example right here. And here's Q. It's less than K, right? So it's going to push your reaction to go towards the products, okay? If K is equal to Q, or Q is equal to K, then the reaction is in equilibrium, right? So there we go, right there. There's Q equal to K, and here's the products and for Q and for K, and they're both at the same point, the equilibrium point. And then on the other hand, if Q is greater than K, nature will proceed to make the reaction go reverse so that you can get closer back to equilibrium. Okay? So let's just remember this part right here, the takeaway message here, right? If K is less than Q, let me say that one time. If Q is less than K, then more products are going to be made. If Q is equal to K, you're at equilibrium. If Q is greater than K, then more reactants are going to be made, right? You're going to go the opposite direction. Okay? So calculating your equilibrium concentrations, right? So we'll go through an example of that in just a second. right? But if you want to know what the equilibrium constant is, you can find equilibrium concentrations from the initials and the changes based on stoichiometry, which we saw that in the previous example, right? You will set up a table, another ice table, and use the one used to find the equilibrium concentration, but the change now will all have x's in it, where you have to solve for x. And I'll show you how to do that in a second. But before we do that, here's your next question. What does nature want? Does nature want Q to be less than K, Q to be equal to K, Q to be greater than K, or none of the above? Oh, I love this stuff so much more than what I'm teaching in my other class. I don't know if you knew this, but I'm teaching uh, a science class, like a general education science class too, in addition to this one here. And right now we're going through, we're learning about electrical motors and magnetism and stuff. And I'm like, oh my God, this stuff is so boring. So if you come to my office and I'm like looking like I'm stressing out with my like face palming and stuff, it's because I'm having to relearn how to do magnetism. It's crazy. I had a terrible physics teacher, so Dr. Walker, that guy. I don't know if you remember this from physics, but there's this point where you have like an electrical current like that, right? And it's going in that direction. And then to show that there's a magnet going, like a magnetic field going, they'll use like X's to show that it's going into the board, and dots to show that it's coming out of the board, the magnetic field. And so these are supposed to represent like tail feathers, as a feather, a tail feather, an arrow is flying through the air. You look at the back of it and you see tail feathers, you know. And so Dr. Walker was drawing those tail feathers X's to show the magnetic field going into the board, and then he kind of stands back and he's like looking at it, and we were like, "What the heck is he looking at?" And then we asked him like, "What are you looking at?" And he starts laughing, just ha ha ha, like megalomaniacally, like laughing. And we're like, "What are you laughing at? Why is this so funny to you?" And he's like, "Oh, I'm just practicing for your exam, meaning all the X's." So that rat bastard. I did not like Dr. Walker at all. He did not make my experience in physics very fun. So see, at least I don't do that to you guys, right? If anything, I make fun of myself. Okay, so let's see how everybody did on this question. Uh, Is that it right there? Q, yes. 10 people answered. And yes, very good. Vast majority have got that one correct there. Only one person got that one wrong. Q needs to be equal to K. That's how nature wants it. Okay? So here's our example. Here's our example. And again, I don't know if you remember Miss Dickens telling you this before, but it's a good time to brush up on your algebra because we'll be using it a lot for the rest of the semester. Um, Buckle up, because it's going to be crazy, right? We have a 1 liter flask. It's filled with one mole of hydrogen gas, right, and 2 moles of iodine gas, just like we did before, right? Given a K of 50.5, right, at 448 degrees Celsius, what is the equilibrium concentration, right, of hydrogen gas, of iodine gas, and hydrogen iodide, right? So just given these things, so you should be able to figure it out. So here's our original ice table, like we saw a second ago, right? Remember that ice is I for initial concentration, C for changing concentration. Some people actually use a triangle to denote change, and then E is for equilibrium, okay? And then of course here we have the reactants again, right? These are the reactants. And here we have the products, and you do what you did before, right? Where you fill in, or the products, you fill in what you know, right? And so initially, 1 goes there again, right, for the initial for hydrogen gas. 2 goes there, right, for the initial of iodine gas. And then 0, because it hasn't happened yet, right? Nothing's happened at the initial. So 0 goes there for hydrogen iodide gas. But we have to solve for everything else, right? We have to solve for everything else, right? So we then know that, remember I told you this on the last one, right? We split this down the middle like that, right? We know that everything over here on the left side is going to be negative, right? And over here, everything on the right side will be positive, right? And so what X is, right? What X is then is the amount of change, amount of molarity that this hydrogen gas is going to lose. That's why it's minus X. Same thing here, minus X, right? Minus X, because it's the amount of molarity that this X is going to lose, right? Or this iodine is going to lose, right? So it's minus X. But then since we know that it's 2 moles of hydrogen iodide for every mole of iodine and hydrogen, right? It's 2 plus X, 2 plus X, plus 2X here, right? Plus 2X here, because there's 2 moles there, right? So it makes sense because if you're losing X here and you're losing X here, you have to gain an X over here, right? And since it's so that's why it's a plus X, but the reason why it's a 2X is because there's 2 moles of hydrogen gas. And then what that means then at the end of it all, the equilibrium concentrations can be solved using these equations, quote unquote. The equilibrium concentration for hydrogen gas is going to be 1 minus X, right, which is the initial minus the X. And then iodine gas will be 2 minus X, which is the initial minus X. And then here, it's just going to be, since you were at 0 for hydrogen iodide, and you're doing plus 2X here, then the concentration at equilibrium will just be 2X, right? Just like that. It's good stuff. It's good stuff. So in our example then, again, we have to do our, our equilibrium constant equation, right, expression, where we have the products, right, the products over the reactants, right, products over the reactants here, right, and if we notice, it's the exact same thing that was at the bottom of the ice table right here, right? We had 1 minus X for the hydrogen gas, so, oops, so there we have the 1 minus X for the hydrogen gas, right? And then we had the 2 minus X for the iodine gas right there, okay? And then we had the 2X for the hydrogen iodide gas, which is right here, okay? And then we were given in the problem that it has a K, or equilibrium constant of 50.5, and that's why we set it equal to 50.5 here. So now what we have to do is solve for all these X's, right? Got to solve for all those. So I'm going to ask you now, how do we solve for those X's? How do we solve for these X's? Say again? That's true. You do have to start multiplying. It's actually called foiling, right? Remember that from high school? FOIL? Close. There's a square root involved. So this is what we call a binomial equation, right? And in a binomial equation, you have to use what to solve for it? The quadratic formula. Do you remember the quadratic formula? Very close. And I'm going to give you a chance to say it before I actually write it out there.
So it's the square root something minus 4ac divided by
2a. That's
2a,
right.
yeah.
Good. So the hodgepodge of all you putting that together got it right. So good job there. All right. So there's a couple of things you got to do first before we can actually put it into the quadratic equation, right? Because right now it's an expanded thing, right? And remember that the quadratic formula requires that you have this format. A equals x, it's not a equals x squared. A x squared plus x bx, right, plus c equals 0, right? It has to be in that form for you to be able to use the quadratic equation, right? It's got to be in that form. Because just like you all said all together, right, the equation is x equals minus b plus or minus the square root of b squared, excuse me, minus minus 4ac, all divided by 2a. Okay? That's the quadratic equation. Okay? That's the quadratic equation. So the difficult thing about this, right? The difficult thing about this will be trying to get this, right? Trying to get that whole thing into the ax squared plus bx plus c equals 0 form, right? That would be the most difficult part of this problem. Okay? So, right? So what do we do first? Okay, well the first thing we should do, right, is try to get it so that we actually have something that equals 0. Okay, we have to make it so we have something that equals 0, right? Because right now we have this part right here is just the expression, right? So really this is the math part right here, right? That's the math part right there. This is the chemistry part, and this is the math part, right? And so really you're going to be working with just this part right here, right? Not the chemistry part, but the math part. Okay. And so when you have it like this, the first thing you got to do is just like Stephanie was saying, the first step is to foil these two to each other. Okay, do you remember what foiling means? Yes, exactly. Right? So, easy as pie, okay? First thing here is we'll do the let me think about this just 1 second here. Okay, yeah. So we'll do, I always like to make it start out looking like the quadratic equation. So the first thing I'm going to do here is I'm going to multiply x times x, right? Because that makes it x squared, okay? And then I'm going to do 1 times x, right? And then 2 times x, right? And both of those are minus x's, right? So that's minus 1x minus 2x, right? Make sense so far? You ever got that so far, right? And then the last thing to do is the 1 times 2, right? Which is going to be the plus 2, okay? And then you still have it equal to, so that part right there is this, right? That comes down to that like that. So now you have this. Oh, I'll go ahead and do this part right here too, where I have to square that up there, right? The 2x squared, right? So all that comes down to looking like this. 4x squared all over x squared. We can combine these two together, right? Oops. Should be negative 3x plus 2, right? And all of that is equal to what? 50.5, right? Oh, say again? Right up here. 2 squared. Yeah. Okay. Everybody got that so far? So now, I don't know about you guys, but the ax squared plus bx plus c equals 0 doesn't have a fraction in it. So we've got to get rid of the fraction somehow. How do we get rid of the fraction? Exactly. Multiply both sides by the entire equation. Right? There. And then you're also going to do the same thing over here, which I ran out of room, but you get the idea. Oop, that should be a minus. Plus 2. Right? So what does that do? That cancels out these down there. right? And now you have 4x squared equals 50.5 times x squared minus 3x plus 2. We're almost there, right? We're almost to the point where we have it equal to 0. Now what do you have to do? We were trying to solve for x, yes. Anybody know what we're doing next? Well, the next step in this is to multiply out the 50.5 to the quadratic formula, not quadratic formula, the binomial equation, right? So you got to multiply 50.5 times this, 50.5 times this, and 50.5 times this, right? So that gives you, I'm going to move over here so I have some room. 4x squared equals, the first one is easy because it's just 50.5 x squared, right? And then minus whatever minus 3 times 50.5 is, which is 151.5x, and then plus whatever 50.5 times 2 is, which is 101, right? So far, everybody got it? Right? Has everybody got it so far? Okay, now I'm at this point. What do I have to do now? What do I have to do now? Keep going. Say again? Subtract 101? There's an easy, what is the point of this whole thing to get it to? So you can use a quadratic equation, right? So what would you need to do to get it to do the quadratic equation? You've got to get it so it's equal to 0. So what do? What about 4x squared? So why, let me ask you this. If you're looking to have a 0 at the end, why do you want to divide it? Right, but you can't use it just yet because it's not equal to 0. So the way you get this to equal to 0, what do you do to get something to 0, anything to 0? Subtract it, exactly. So subtract minus 4x squared on both sides. I told you we're going to do a lot of math now. Class? That's great. It's going to be perfect for you then. You're learning it here and you're learning it in your other class, right? It's great. So we do that, right? We subtract both sides. That makes it so this side over here equals 0 already, right? So this is, I'm running out of room, so I'll just write it over here. So the left side now equals 0, right? And now the right side equals what? What is 4x squared? What is 50.5 x squared minus 4x squared? 46, exactly. So 0 then equals, right? 0 then equals 46.5 x squared, and the rest of it stays the same. Why can't we do any more subtracting? So I can't hear you. Say that one more time. Exactly. That is exactly right. We've already combined all like terms, right? Because x squared is a like term, x is a like term, and then there is no thing for that one, right? And so now you have this equation right here, which is great because now it's in the form of what? Ax squared plus bx plus c equals 0, right? Good stuff. Good stuff. I tried to warn you guys, right? We're going to be doing a lot of math. Well, if you're really good at it, it actually goes by really fast. I mean,
Changing my major.
okay, so now let's solve for x. Okay, let's solve for x. Now let's solve for x. Okay, so I'm gonna erase some stuff here so I have some room. If that's okay with you guys. Maybe not, because that might confuse you some more. Okay, so now we can use the quadratic equation, which is right there, right? So it should come out to be this, x equals, right? And I'm using this one again just to make sure, the quadratic equation right there, right? Minus 1, negative 155.5, okay? Don't forget the plus or minus part, okay? The square root of, again, negative 151.5 squared minus 4 times 46.5, because that's A, times 101, because that's C, right? All this is divided by 2 times 46.5. So now all you have to do is plug that in your calculator and figure out what the answer is, okay? I'll try to make so that you can see this on the notes. Separate all this out for you. There we go. Okay? All you have to do is plug that in your calculator and you can figure out what that is. And see, the thing about it is that I cannot stress enough how important it is for you to do. Please excuse my dear Aunt Sally, or the order of operations here, okay? Okay? You should get two answers. One of your answers is going to be, well, actually, if you're calculating it, let me see. And don't worry, if you don't have a calculator for the exam today, Ms. Dickens will have a box of calculators for you to use. But you absolutely can't have a phone, all right? All right, I'm going to go ahead and give you the answers, and you try to do this and see if you get the same thing, okay? You're either going to get x equals 2.323 or x equals 0.935, okay? So far, so good. Are you guys getting the same answer? Let me make sure I'm still recording here. Are you still recording? Are you still recording? Yes, you are still recording. You can still hear me. Okay. Don't forget to use your parentheses. Don't forget to use your, things. Okay. As soon as someone tells me that they have a similar answer to mine, I'll move on. Did you get a similar answer to mine?
I got the same answer.
Good. Did you actually use the, did you actually do the quadratic equation piecemeal like that, or did you use the binomial function on your calculator? If you didn't know this, a graphing calculator actually solves quadratics, binomials, quadrinomials, trinomials, and all you have to do is plug in the A, B, and C. Yes, they can. But that's the reason why you're not allowed to use them on exams, right? I'll show you later. But yes, there is a function on graphing calculators that allows you to just plug in. Yeah, all you do is plug in the A, B, and C, and it calculates it all for you, right? But it's important that you do it this way because that's how you're going to be doing it on the exam. You're not allowed to have a graphic calculator on the exam. All right, so Naraya's told me that she's got the same answer as me, so we can move on. Let me ask you this question now. Which is the correct answer? Oh, first question is, why do we get two answers? Huh? We do have a plus or minus. That's the one reason why. But what's the other reason why? What does the graph of an exponential equation look like? A binomial equation look like? It's a parabola, exactly, right? It looks like this. Someone knows stuff, right? I know what she's talking about, right? It's either going to be like this, right? Or it's going to be like this, right? And when you're solving for x, you have an x there, and an x there, or an x there, or an x there. And so you have two x's you get, right? That's why there's a plus or minus. Make sense? So how do you know which one's the right one for the chemistry part of the question? Right. Yeah, because like once you get over here, right? It tells you right here that you have only 2 moles of this and 1 moles of this, right? And this is a change, correct? That's a change. You have to minus that. And one of your answers is 2.32. Is it possible to subtract 2.32 from 1 molar or from 2 molar? No, because that's you don't have that much, right? So what's the correct answer then? Yes, the correct answer is 0.93. Oh, forgot to put the drawing mode. So the correct x is this one, right? The 0 point, the correct x is the 0.935, right? Does that make sense? That's the correct x. The incorrect x is that one, right? Because it is physically impossible for you to subtract 2.323 molar from an initial concentration of 1 molar or initial concentration of 2 molar, right? So it's always going to be the number that's less than what your initial concentrations are. Does that make sense? It will always be the x. The x will always be the x that is lower than your initial concentrations. Okay? Think about this, right? In math, they just give you numbers and you just figure things out. But in chemistry, it's about problem solving, right? So you've got to use your common sense and figure out what's not possible and what is possible, right? It's not possible to subtract 2.323 molar from 1 molar or from 2 molar. But it is possible to do what? Subtract 0.935 molar from 1 molar or 2 molar. Does that make sense? You've got to think about this in chemistry terms, okay? So, good stuff, right? So just like Narayan just said, let's plug it all in. Okay, let's just plug it all in. Right? Since x must be subtracted from 1 molar, 2.23, 2.323 makes no physical sense. You get a negative concentration. Crazy, right? Absolutely crazy. Okay, so the value must be the 0.935. So in the end, all you have to do now is subtract that change from, because remember the equations were right. Remember that it was in the ice table for this one right here. It was 1 minus x, right? And this one was 2 minus x, right? And this one was what? Remember what this one was for hydrogen iodide? It was just 2x, right? Okay, so all you do now is you plug in the 0.395, 3.395, no, wait, 0.935 into that x, into that x, into that x, right? And when you do that, you end up with your answers, your equilibrium concentrations, right? You end up with your equilibrium concentrations. Isn't this amazing? It's amazing stuff. It's so cool, right? It's so cool. And you know what else it's so cool too, right? Because when you look at the what it was originally, right? This is what you had right here as the equilibrium, right? You had all these x's right there as your equilibrium. You come over and do the quadratic equation, right? And then you get these answers here, right? And look at that number right there, right? It's actually off the order of magnitude of the same number, 1.87. Isn't that crazy? Crazy stuff, right? Crazy stuff. Okay. All right. Any questions on that? That was mostly quadratic stuff and and math stuff, right? Any problems? Any questions on where that comes from or anything like that? I expect the people that just came into the class are probably gonna have to watch the video for this one, right? So good luck. But no, I explained it great. I promise. I think I did anyway. It's just basic algebra. Okay. So here is your next question. When solving for x, what mathematical formula is used? When solving for x, what mathematical formula is used? I've got 8 responses. I'm waiting for 4 more. 4 more responses. 3 more. 2 more. 1 more. Okay, I've got everybody's responses. What is the correct formula to use to solve for x? Quadratic equation, exactly. Right? Quadratic equation. All right.